Cyclotron was invented by Lawrence and Livingston in the year 1934 for the purpose of studying nuclear structure. Cyclotron is a charged particle accelerator, accelerating charged particles to high energies. Principle: when an ion moves perpendicular to uniform magnetic field repeatedly, magnetic field puts the particle into circular path. Whereas, high-frequency electric field applied perpendicular to magnetic field accelerates it. As a result, frequency of revolution of charged particle does not depend of its energy, but the charged particle gets accelerated to high speed and gains sufficient large energy. Construction: in a cyclotron both electric and magnetic field are used in combination. These are applied perpendicular to each other in directions. Cyclotron consists of two semicircular disc-like metal chambers, D and D2 called Ds, as shown in Fig. A uniform magnetic field B is applied perpendicular to plane of the Ds. An alternating voltage up to 10,000 volts at high frequency 10 MHz is applied between the two Ds. Positive ions are produced by a gas ionizing source kept at a point P in between the two Ds. The electric field provides acceleration to the charged particle. Once the ion is emitted, it accelerates due to negative voltage of a D and performs a semicircular motion within the D. Whenever the ion moves from one D to the other D, it accelerates due to the potential difference between the two Ds and again performs semicircular motion in the other D. Thus the ion is acted upon by the electric field every time it moves from D to other D. As the electric field is alternating, its sign is charged in accordance with the circular motion of the ion. Hence the ion is always accelerated. Its energy increases and the radius of its circular path also increases, making the entire path a spiral. As electric and magnetic fields in cyclotron are perpendicular to each other, they are called crossed fields. Magnetic field in cyclotron is produced using an electromagnet producing a field up to 1.5 T working. Consider an ion source placed at P. An ion moves in a semicircular path in one of the Ds in a time interval t2, T being the period of a full revolution. Using the cyclotron formula, mv equals qbr. T equals 2 pi r, Vt equals 2 pi m, qb. The frequency of revolution, i.e. cyclotron frequency, is f equals 1, Tf equals qb, 2 pi m. The frequency of the applied voltage between the two Ds is adjusted so that polarity of the two Ds is reversed as the ion arrives at the gap after completing one semicircle. This condition is the resonance condition. The ions do not experience any electric field while they travel within the D. Their K increases by EV every time they cross over from one D to the other, where V is the voltage difference across the gap. The ions moves in a circular path with successively larger and larger radius to a maximum radius at which they are deflected by a magnetic field so that they can be extracted through an exit slit. From equation 1, V equals qbr per meter. The K of the ions, protons, will be K equals 1/2 mv squared, K equals q squared b squared r squared. 2 meters. The final energy is proportional to the square of the radius of the outermost circular path. Application: cyclotron provides high energy, MeV to JV, particle beams which are useful in studying particle matter interaction as well as in medical treatment of tumors and diseases.